Deviations from the TCP/IP architecture, and this is what makes it sometimes hard to understand. When you read the user manual of a box, usually you have to understand the specific terminology of the user manual, which is often not correct. Plus, you have to understand that it does things that are not according to the architecture. Here we will see a number of things that are either not according to the architecture or, like fragmentation, are in the architecture but are a bit weird. So we'll talk about fragmentation, then interworking, IPv4 with IPv6, which in principle is impossible, but in practice is possible. How can we translate an IPv4 packet into an IPv6 packet? And then even stranger things like proxy ARP, which is perhaps hard to understand if you want to be logical, but easy to admit if you accept the fact that things are hacked more than designed. Fragmentation is the fact that there is not a unique size of the physical layer or the MAC layer. Here I'm listing almost complete set of packet sizes that exist. The standard packet size is 1500 bytes. That's the value we've used very often. But there are lots of technologies that have different values. For example, you have jumbo sizes that are used in the in the physics experiment at CERN, when they do at least high volume of data. Then they create IP packets that are much larger because the traffic is huge and it's always repetitive with huge amount of data. Then you have also older technologies that have smaller packet sizes and more or less exotic, more modern or ancient modern technologies that have larger packet sizes. The result of this is that when you send an IP packet from a machine A to the other end of the world, it may be that along the path there might be links where the packet is too big to fit on that link. If that happens, we will do what is called fragmentation. So the fragmentation is performed when a packet is too large. So I'm giving here an example, but before giving the example, first principle of IP is that fragmentation is done at the IP layer. So when TCP or UDP passes a packet that is too large somewhere, it will be broken. That will be done by the IP layer, which means the receiving end will not notice whether there has been fragmentation or not, or the receiving program at the other end. The second principle, if you fragment a larger packet into several pieces, of course, you will need to reassemble somewhere. Reassembly is always done at the destination, never at intermediate routers. Let's look at an example. So I start with a packet here, and I assume I have an MTU size of large enough for this packet, and then I hit a network that has an MTU of 620. So this packet is too large. What will happen to this packet? It will be fragmented. Now, how is it fragmented? Well, with IPv4, it will use a number of fields that are illustrated here in the IP header. In IPv4, fragmentation was considered to be something that you expect to occur. With IPv6, we expect it to be a rare thing. So with IPv6, it's an extension header. With IPv4, it is in the regular header. In the IPv4 header, there are fields that help find out the bits and pieces of a packet that is fragmented. The terminology is the original packet is called a datagram. When it's fragmented, the fragments are called pieces of a datagram. Each of the pieces is a standalone IP packet. So when you break an IP packet, an original IP packet, a datagram into 3 pieces, you obtain 3 standalone datagram. You don't obtain something that has a header around it saying, oh, this is a piece that has been broken. So it's the same IP header. The 1400 bytes will be split into a first packet that is here 600. And inside the IP header, we will find fields that help us understand the fragmentation. So here I'm showing first the packet will be broken into 3 pieces. And if we look at the piece 2A, so the first piece here, we will see that it has a length of 620 bytes, An identification, so what is the identification? Identification is, is a number given to the original datagram. So whenever an IP source generates a packet, IPv4, it puts a number to it. The number doesn't mean much, it's used only for fragmentation. And for every source IP address here, the packets are numbered by incrementing by 1 for every new packet sent. So this packet has received the number 567. The 3 fragments will have the same number. This is what will be used to glue them together to be able to recreate the same packet. Then there is an offset which says where in the original block of data, this block here. Here is the first, so the offset will be 0. And there is a more fragment bit that says whether there is more, which means whether it is not the last. So here there is more, so the more bit is put to 1. So those are the fields we will see in this one. This original packet had no fragmentation, so it's visible by the fact that the more fragment, the more bit is 0, there's not more, and the offset is 0 also. The second and third packet, so this was for 2A, 3A, that's the first. So for 2B, for example here, we will see that the more bit continues to be 1, and the offset is 600, because there are 600 bytes before. So the offset for this one is 600. And for 2C, do I show 2C? Yes. For 2C, the offset is 1200. And the more bit for the third packet is 0, which means it's the last. For some reasons, we can save 3 bits by coding instead of the offset. We code the offset divided by 8, which saves 3 bits because we assume that the fragmentation always occurs by multiple of 8 bytes, words of 64 bits, which was a hindsight. This is the classical word for modern computers, word size for modern computers, so it was anticipated here. Then when the packets arrive, it can be that each of the 3 packets is now a standalone packet, so it's routed through the internet. There might be parallel paths. It might be that the first packet that arrives is 3B. Then when this host receives 3B, it will know that this is a fragmented packet because the offset is non-zero and the more bit is 1. So it knows it's a packet that's in the middle. So it will start constructing in a buffer this packet by putting it at offset 600. When 3C comes, it will write the 200 bytes at the end of this one. And it still knows I don't have a complete packet because I know this is the last, because the more bit is equal to 1. But I know it's not complete because in my buffer, I have not received anything for the first 600 bytes. So only when and if this arrives, the fragment will be reconstructed and delivered to the upper layer, which might be UDP or TCP here. If any of those fragments is lost, what will happen? Well, this machine here that's trying to reconstruct will time out, typically. We'll wait a bit of time. Now, packets don't live so long. You don't expect a packet to live through the internet for a minute. You expect it to live for perhaps a few seconds. So the reassembly mechanism has a timer, and if any of the fragments is lost, then this will time out, and the entire datagram is considered lost. That's what it means when we say it's done at the IP layer. So I think I've explained all this. So for IPv6, it's the same with a modification. In principle, with IPv6, routers never fragment. In the example I gave here, it was the router R1 that fragmented. In IPv6, that will never occur. In IPv6, we consider fragmentation as a thing of the past, so we don't do it. But sources may be able to do it. Why would sources still need to do it? Well, because we want to keep the datagram orientation of UDP. Remember, UDP provides a datagram service, which means that with UDP, you know that the message that you receive is the original message. Unlike with TCP, when you do a read from a TCP socket, you don't know whether you're reading part of a message or several concatenated messages. When you do, in contrast with UDP, if you do a read, you know you get exactly one message. Now with UDP, if you do this, you want to have allow for a message size that may be larger than the MTU. So with UDP, you can have packets that are much larger usually than the MTU, up to 64K bytes, I believe. Then, if UDP issues a datagram that is larger than the MTU size of this machine, then it will be fragmented at the source here. We don't want routers to fragment because it's a lot of work for a router to fragment, and we want routers to do as little work as possible. We expect also with IPv6 that fragmentation is less interesting anyhow because IPv6 mandates a minimum MTU of 1280 bytes. Now you can wonder why not 1500? Most modern technologies are with 1500 bytes. In fact, even with Ethernet, it may be that your MTU is less than 1500 bytes. Could you imagine a reason for that? A reason that you can see today if you're on your machine? Yes? Tunneling, exactly. For example, if you access EPFL wireless with a VPN, then a VPN means that your IP packets are encapsulated in things that contain encryption and security and other things, which reduce the original packet size. So you add headers, a few tens of bytes usually per packet. So the maximum packet size will be 1500 minus all that stuff. So it can go down to 1400 bytes for classical VPN tunnels. So IPv6 is on the safe side. It's let's assume we do lots of encapsulations, perhaps 2-3 times. Then we can go down in the very worst case to 1300 or 1280. I don't know how they came to that number. Since this number is fairly large, this is practically the packet size that is used over IPv6. Very often, most applications, we use this packet size by saying that one is safe. Because what happens if you have a system where routers don't fragment and a packet is too large, then what will happen? Packet will be dropped. If you have a polite router, it will send an ICMP message back to the source, like we use when we do trace routes, for example. With trace route, we have ICMP error messages because the TTL is too small. There is similar an ICMP message that says packets too large. Then if you get this message back, then you know the packet is dropped because it was too large, so the application should reduce the size here. But not all routers support ICMP messages because it was used and misused by attacks. Fragmentation, like redistribution, is usually considered harmful, so we try to avoid it. Why is that? Well, first, the reassembly at destination is not a nice thing. We've said you use a timeout. Now, if you frequently drop pieces of a datagram, that means that the operating system at the destination is bugged with lots of datagrams that are trying to be constructed but will not be delivered. That's a recipe for congestion collapse, if you remember. Congestion collapse occurs easily when you have systems that are busy doing things to pieces of work that will not complete. Here, you might have a system that's busy trying to reassemble, busy with CPU cycles, but probably more importantly with buffer size. And if it's a big server, then it's easy to do a denial of service attack. It's easier, it multiplies the impact of a denial of service attack. So we try to avoid it as possible. There's also worse if we use fragmentation with TCP. Imagine I send one TCP packet, a TCP segment of 15 or 1400 bytes, and it's fragmented into 3 pieces by the IP layer. Assume one of the pieces is lost. What will happen? The piece is lost. That means the datagram at the end is not reconstructed. So the 3 pieces will not be presented to TCP. TCP will consider that the 3 pieces are lost. So we send 3 pieces, we lose 1, we repeat 3. Sooner or later, TCP will retransmit the 3. Which means that we've amplified the loss rate. Instead of dropping 1 out of 3 packets, the effect is the same as if we had dropped 3 packets. So we multiply by 3 the loss rate. Right? Now, if we multiply by 3 the loss rate, we might cause more congestion because if the loss rate was due to congestion, then we might cause more retransmissions, and this has, in fact, that was one of the reasons for the congestion collapse in the internet in the mid-80s. It was combined with the fact that there was no congestion control mechanism in TCP, and there was fragmentation. So those two things combined together has called an avalanche, and that caused the congestion collapse. So we want to avoid that. In principle, TCP should avoid this, and the way to avoid this is to do what is called path MTU discovery. Path MTU discovery means that the end-to-end, the two ends of a communication, in particular when we use TCP, try to infer what's the maximum packet size that works on this link. It's used primarily for IPv4. In IPv6, what many systems do, they say, let me assume that 1280 is the MTU size, and because it's the minimum MTU size, and in many cases it's close to the maximum anyhow, so you don't bother. For IPv4, it is typically done. One classical way to do it is to rely on ICMP error messages. You try, there are not such a large number of possible sizes. I've shown practically an exhaustive number of MTU sizes. So you try the largest that is possible, so the size of your interface, if you're on Ethernet, 1500 bytes. You try to send packets. If you get an error message, you decrease. And if you still get an error message, you decrease again. And once in a while, like nasty children, you need to increase, try again the thing that did not work before, just to see if you get the same punishment. And if you don't get it, then you can do it. So here, this is to avoid being locked into a small path MTU, if that was caused, for example, due emergency rerouting in a network. That very often doesn't work because of ICMP, so there is TCP support for that. So there is one of the zillions of mini algorithms that are added to TCP is called path MTU probes, or path MTU discovery, which is essentially the same but relies on TCP voluntarily once in a while trying different packet sizes and see if it works. Right? The path MTU is in principle always shown for any destination. So here is, for example, a dump of path MTU. Where is the value of the path? Yeah. Well, this is a dump, not very exciting. On my machine, then I have a path MTU of 1500 for all those destinations, which are kept here. Which means that when a host sends a packet to a given destination, if it's a modern host, it will know what is the maximum MTU that it can use to avoid fragmentation, because we consider it's bad. TCP should always avoid fragmentation, and as I've discussed, UDP accepts fragmentation, but in principle, will try to do it at the source only. A little question. Assume a host generates UDP packets, for example, a video, real-time video, or industrial PMUs, and we capture some packets. Will we see the port number in all packets? I close in 5 seconds. And for this time, the majority is wrong. The correct answer is, oops. Voilà, here we are. The correct answer is number 2. Why is that? Oops. If you fragmentation is done at the IP layer, so UDP writes a UDP header, puts the data, passes that to the IP layer. If the IP layer does fragmentation, then it takes the header is in the first packet, the rest doesn't contain the UDP header. So if you intercept the second packet, you will see that it is UDP because the IP protocol type, which is in the IP header, will say it's UDP. But if you have a non-zero offset in the fragment, what is at the beginning is not the UDP header. You're just in the middle of the data. So you don't know what the port number is. Right. So if you are a classifying router that is trying to classify flow by looking at the port number, you will probably complete, that won't work here. It's one of the drawbacks of fragmentation. If you want to kill all the IP packets that go to a given port number, like most firewalls do, it will still work because you will kill only the first the first fragment. The other fragments will not be killed. If you look at the port number, you will find a number in the UDP space, but it will be just random bits. So chances are you will not kill the other packet. But if you kill the first fragment, then it's like killing the entire packet. You will still transmit the following fragments, but not that one. So fragmentation is not desirable, right? With TCP now. I close in 5 seconds. And the correct answer is the majority. Showing here what can happen if we use TCP for that. If this fragment is deleted, then there will be no reconstruction. So TCP will see 1400 bytes or minus the TCP header missing. So it will retransmit everything. This is why fragmentation of IP packets should be avoided with TCP. If we have a mechanism that can retransmit selectively some bytes, then it's stupid to have to retransmit everything when a fragment is done. Voila, so let's continue our exploration of the dark face of IP, if we want, with IPv4 versus IPv6 interworking. So this, I'm just repeating what we've said a minute ago, and we've seen one solution to the interworking, which is an application layer gateway. Now there is another solution, which is more in line with the end-to-end principle of the internet, which is called NAT64. NAT is a NAT, the Network Address Translation Mechanism, and 64 means between IPv6 and IPv4. So we are in a situation like this. I have a machine that is on the IPv6 internet, and another one which is on the IPv4. And let's assume it's the server, it's a client-server interaction, and the server is on IPv4, the client is on IPv6 here. Now, we would like that the client is able to go natively to the server without having to go via an application layer proxy. Well, the idea is to say, well, it's very similar to the problem I have at home where I replace the IPv6 internet by my private network at home. I mean, most residential networks are using private IP addresses, IPv4 addresses, 10 dot something or 192, 168 dot something. So if you are using those private addresses here, in order to go to the public internet, we use a NAT. Well, we can use the same thing here. We can treat the IPv6 internet like a private address space compared to IPv4. That's the idea of the NAT. Now, there are some things that are special due to the fact that it's IPv6 that we will see. A bit of terminology. With this way of operation, we will give the illusion of to H6 that the server with whom it speaks is an IPv6 server. We must do that. There's no alternative because this guy speaks IPv6 only. So it will send IPv6 packet to that server, which means also it will believe this server has an IPv6 address. You will need to put an IPv6 destination address. And similarly, this guy will believe that it's talking to an IPv4 host, and it will speak to it to an IPv4 address. That's the same we do when we have IPv4 private addresses. When I go to a public server, I don't show my 10 dot something address. I show a public IPv4 address to this guy. So this guy believes I am I am a legitimate thing. Now what is different is that in the case of private to public IPv4, here there is no problem to translate the server address. Here we will need to do translation on both sides. We will also use port translation because we will use an IPv4 address pool. What does that mean? IPv4 address pool, it means it is all the set of addresses that, if you want, are here at point 2 that represent all the IPv6 addresses that are behind the NAT. When you're at home behind the NAT, you have an address, which is a Swisscom address, for example, and this Swisscom address can represent many of your private addresses. So here is the same thing, except we will not use not one single address, because that will not be sufficient. We will want to serve a large number of IPv6 customers, so we will have a pool, a block of IPv4 addresses. And as we will see, in the reverse direction, we will not use. Playing animation. Okay. So how will it work in practice? Well, the NAT is stateful, so it will need to remember some of the mapping. So I'm showing here the example. The NAT, the pool that is used is this. So it's a block of 24-bit, 120, 130, 26. Those are all the IPv4 addresses that will be allocated, fake addresses allocated to the IPv6 hosts. So when a packet comes from an H6 host, it will reach the NAT. We will see how. Then the source IP, so it will come via IPv6. Of course, the NAT is dual stack. It has one IPv6 interface, one IPv4 interface. So it has a source IP address, which is an IPv6 address. This one will be replaced by a source IP address, which will be one in this pool here. That's the same thing as we do in the NAT we have seen before. So if this packet comes from that address, this long IPv6 string, it will be translated to this address. And because we don't want to reserve one IPv4 address for every separate IPv6 address, we may use the same address several times. We will also do port mapping. So we will translate the port number so that we can reuse this same address for multiple IPv6 hosts here. So it is a stateful operation. And when the server here will receive a packet, it will receive a packet with this source address. So it will respond back to that address, and it will reach the NAT back that now has remembered this. So it will now, in the destination address field, it will put destination address equal to this one and destination port number this for the reverse direction. So that's half of the story. Now in the reverse direction, then the question is, how do I map that address as a destination address to this one? Here, the answer is simple, because the IPv6 space is huge. So we can embed the IPv4 address space into IPv6 if we choose a well-known prefix. So there are usually ISP-specific prefixes. I wrote here IPv6 Internet. This is not typically done. You don't NAT between anybody and anybody. This is usually within a provider domain. So if you're IPv6 Swisscom, you do this for Swisscom customers only. There is a default block, which is a 96 prefix, which by default is this one. Why 96? Because 96 plus 32 gives 128. So this is the number of bits you need to add to obtain, to go from IPv4 to IPv6. But you can use any other prefix if you prefer, as Swisscom, to use another one. So that means this well-known prefix means IPv4 seen from IPv6. So when this host will send a packet to that server, it will send a packet with this IPv6 destination address, where you recognize C00201, that's the hexadecimal representation of this address. So for the machine, it's the same address. The last 32 bits of this IPv6 address are the IPv4 address. So we put an IPv4 address inside an IPv6 address. Now the good news for this is that this mapping is completely trivial. So it is stateless in the sense that the NAT doesn't need to remember anything. When a NAT receives a packet here, it has to do something for the source IP address, but for the destination, it simply removes the 96 first bits, and it gets immediately the destination address. And similarly, in the reverse direction, when it gets a packet from this server to that destination, it can immediately do this stateless operation. So that may seem a bit confusing. Let's see if you're able to answer this question. So this address translation occurs presumably when we have in this direction a packet where this is the destination, where this is the source address, 192, yeah, when this is the source address, or in this direction when this is the destination address. In both cases, we need to translate. How is it done? I close in 5 seconds. And of course, it's algorithmic, as we have said. This was just a small verification. There is nothing to do, nothing to remember because of this well-known prefix. Now, of course, what I have not explained is how do we know that we should go via the NAT, for example. Well, typically, again, this is DNS that plays an important role. So this client here wants to go to this server, probably not because it knows the IP address. If it knows the IP address, then it can directly use this encapsulation, though this might require some configuration. But most of the time, you go to a server by the name. So if you use NAT64, you need also to put in your DNS server the corresponding mapping. So you need to manipulate your DNS server, which is typically done if you're an operator. Then if you use the DNS of the operator and not the one of Google, then it will work. So when client asks for what is infoscience.epfl.ch, for example, then it will go to the DNS server. Now the DNS server knows, oh, I have a client that is in my IPv6 only domain. Poor guy. He has to go to InfoScience that works only on IPv4. But of course, I will not, if I had an IPv4 client, I will give the IPv4 address, but this is an IPv6 only client. So it doesn't help to give the IPv4 address. I will give an IPv6 address, and I can map it directly. The DNS server doesn't need a special table for that. It just needs to be configured with the same prefix, this 96-bit prefix. It will translate for me the IPv4 address into an IPv6 address. And from there, this guy does not know that it's talking to an IPv4 server. So from there on, you are communicating with an IPv6 server, at least at the IP layer. You have obtained an IPv6 address, which is the beauty of this thing. It's transparent to client 6. Right? So if we put things together, this is what we obtain. We will map the IPv4 address and IPv6 address, which is very convenient in one direction. And then we will also map the IPv6 address to IPv4 address. But to do that, we need the same trick of NAT with port translation here. one question again, how will the NAT translate the IPv4 address to an IPv6 address? I close in 5 seconds. And the correct answer is the majority. Here we're using an address from the pool. Here that is a pool of fake IPv4 addresses. So this pool is probably smaller than the number of clients we want to serve. So we need to use the classical NAT trick with the table and the help of the port numbers. Well, this is our first approximation of IPv4, IPv6 interworking. We will see more next week because unfortunately this solution as it stands is usually not the one, or is not always the one that's deployed here. In particular, it doesn't work well. It works in one direction if the client is on IPv6 and the server on IPv4, which is the problem you have if you deploy IPv6, for example, in a cellular network where there's not enough IPv4 addresses. But what do you do if you have the reverse direction, or if you want to do Skype? If both are clients, you want to do Skype from an IPv6 only machine to IPv4, right? We'll talk about that next week. In that case, you need some additional trick. Let's skip that. And let's go. Proxy ARP is one of the weird things that makes sometimes MAC address and all that stuff very hard to understand because it's really cheating. Remember the principles of internet, of the IP. Subnet equals subnet mask. So a LAN equals a subnet equals a given network subnet prefix. So if you have two different sides of a router, they should have different subnet prefixes, right? What if you want to cheat a bit? For example, if you want to put on ETH0, which is one of the interfaces of R3, you want to put this machine, 12.12.12, that has an IP address which is completely invalid. It belongs to this one. Right? So again, that's wrong. You should not do it. But if you do it, perhaps there's a way to make it work. Certainly in the routing table, you can do routes that are called host routes, where the prefix is equal. The prefix is equal to the total IP address. You can always manipulate the routing table so that when a packet comes here, instead of going to the 12.12, for this specific thing, it will go there. It is possible because IP does longest prefix match. However, as we will see, it poses a number of other problems. Here is a real-life case that is not so much used, but is still existing at EPFL. If you want to access EPFL via modem and PPP, perhaps because you're in Syria doing a special experience and you have only satellite access over satellite telephone, then you would go to a box called SIG 500CS, which you call by telephone, and that is connected to the rest of EPFL here. When you do that, of course, you must start your VPN client or something like this, and then you will get an IPv4 address, which is, if you observe it carefully, is an IPv4 address that belongs to this subnet here, to the .84 subnet. Therefore, what do you think? Should SIG 500CS, should it be a router, a bridge, or an application layer gateway? I close in 5 seconds. I'm not closing. Well, the correct answer is the bridge. It should be a bridge. At least that's the correct answer if you want to have full grade at the test. Because the theory says if you have the same subnet on both sides of a machine, it cannot be a router, because that violates the principle of IP. So in some sense, you are right. Now, assume you want to cheat. In this real world, we can cheat. And you want it to operate as a router. If you do that, you're cheating somewhere. So you will need to manually or by some other procedure compensate the cheating that you've done. If you cheat once, you have to cheat at least twice, and sometimes even more. That's the tragedy of cheating, right? You're caught into a bad direction. For example, assume we cheat. We say this guy cheats by putting host routes. Like we have said, you can put host route. The SIG 500CS router can say this address 84.133 is to go on that north port and not on the south one. So this I can do. But now the problem will be here. If this guy has a packet to send to, if ED0X has a packet to send to me, to Green Mac, he will do an ARP, because by the principle of IP, it is on the same subnet as this interface. So we'll need to find the MAC address of this. What do you think should happen? What should you do for the system to work? I close and free you in 5 seconds. Then this guy should respond with a MAC address. So who can respond to the ARP? Well, certainly Green Mac cannot, because anything that it does will be received first by SIG. And probably if you're connecting over a satellite link from a very, very remote and complicated country, you don't want to send the broadcast ARPs over the satellite link, so it will not. So who needs to answer? Well, it's 6500CS. And it needs to answer with a MAC address, which is its own MAC address. Because if it responds with the MAC address of Green Mac, it doesn't help, because the packet should be forwarded at the MAC layer to 6500CS. Well, this is exactly what is called proxy ARP. Proxy ARP means, in a case like this, you respond for someone else's MAC address. You can try it at EPFL. EPFL, the last time I checked, it worked. If you configure wrongly your subnet mask as being 16-bit instead of 24, it will work, because all routers will do proxy ARP. If you do this, you believe that the entire EPFL is one big subnet, so any EPFL destination is on link with you, so your machine will send an ARP for any destination. But the next hop router will respond with his own MAC address. So it will continue to work. Voilà, that's all for today. Tomorrow, a test on BGP.